Good morning, everyone. My name is Vitale. I am a postdoc at University of Cyprus. And today I'm going to present an overview on the Caramel project. Caramel is a European funded project that started 8 months ago. So today I'm going to present the preliminary proposal of Caramel for a secure architecture for connected and autonomous vehicles. The motivation behind Caramel is quite simple. In the recent past, several new technological domains have been adopted in modern vehicle mobility. And therefore, new cybersecurity gaps have been introduced. Caramel aims at addressing such gaps with the introduction of advanced techniques, mainly based on machine learning and artificial intelligence, that are able to detect and possibly mitigate such cyber threats. Another important result of Caramel is the anti-hacking device, which is basically a physical controller integrated into the vehicle that runs pre-trained models on the normal behavior of the system so that the vehicle can validate in real time the measurements of the sensors. A second important role of the anti-hacking device is the one of validating the software running in the car PC, as for example, the embedded application platforms. The activities of Caramel are organized into three pillars: autonomous and electromobility, which we will briefly describe in this presentation, and connected mobility, which instead will be the focus of this presentation. So let's start with the first pillar of Caramel, which is autonomous mobility. As you may know, the Society of Automotive Engineers introduced 6 different levels of automation for a vehicle. In Caramel, we focus on full automation, which basically means that the vehicle is able to perform all driving tasks, at least under certain conditions. For this type of automation, the type of attacks that can be carried out are 2. One in the environment where the vehicle is moving, and another one is instead on the vehicle itself. For the first type of attack, in Caramel, we focused on attacks on traffic signs. So basically, an attacker modifies the traffic signs on the road infrastructure with graffitis or with more advanced techniques, as for example, machine learning-based techniques, so that the task of recognizing the traffic signs for the vehicle becomes much more difficult. The second type of attack is instead more invasive and is on the output of the sensors inside the vehicle. One of the possible attacks of this category is the one that I present here in the slide, where an attacker is able to modify the output of the camera sensor, few pixels. Actually, the human eye cannot recognize what has been modified. But this modification is such that the vehicle does not understand anymore what's going on in the environment. In this specific case, the vehicle is not anymore able to perceive the presence of pedestrians in front of itself, but instead it believes that there is a clear way and it can go without any problem. As solutions, in Caramel, we propose robust training, machine learning-based robust training, and the fusion of different sensors measurements. In the attack I mentioned before, with LiDAR, we may actually be able to perceive the presence of the pedestrians and therefore raise concern on the validity of the camera feed. For the second pillar of Caramel, instead we focus on electromobility, and specifically on the scenario where vehicles ask for the battery recharge. In this scenario, there are many actors involved, from the power operator to the operator that deals with communication, the service operator, and therefore there are many weak links where the attacker may place a threat. Specifically, we focus on the syncing of all the requests of the electric vehicles connected to the grid at the same time for battery recharge. This basically creates a fictitious peak in the demand for a power operator and possibly huge problems, as for example, a blackout. In this type of attack, we focus on a solution which is decentralized. We basically impose that neighboring vehicles communicate with each other and schedule their battery recharge not at the same time, no matter what is the condition in the system. Finally, for the third pillar, in Caramel, we focus on a novel secure infrastructure for the communication of connected and autonomous vehicles. The key aspects of this infrastructure are four: multi-RAT capabilities, a MEC platform, a PKI infrastructure, and the already mentioned anti-hacking device in the onboard unit of the vehicles. Specifically, for multi-RAT capabilities, what we mean is that the vehicle can choose, depending on the scenario, how to transmit its traffic both with cellular network and 802.11p. The MEC platform in our architecture not only plays, as mandated by the ETSI standard, the role of soft router for the traffic, so it basically decides how to steer the traffic in the communication network, but it also hosts MEC app, which basically enable the possibility of cooperation between vehicles, but also it enables a centralized view of the system, which is obviously much more complete. The third key aspect of this infrastructure is the PKI infrastructure. What we envision is that the presence of traffic in this communication network is always encrypted and signed by the transmitter. In order to achieve this goal, we introduce the PKI infrastructure I mentioned earlier. The most important entities we have in this PKI infrastructure are three: the enrollment authority, the authorization authority, and the validation authority. So every time a vehicle enters in the system, asks for a certificate to the enrollment authority. The enrollment authority distributes the so-called authorization tickets to the vehicle so that the vehicle can start transmitting in the system. The authorization authority instead manages this kind of certificates, while instead the validation authority is the novel part of this infrastructure and is the authority that takes care of transmitting to the vehicles a list of revoked certificates. In this way, basically, we can say to the vehicles and all the other entities in the system which data to trust and which data not to trust, because basically we are announcing a list of vehicles which certificate was revoked. The fourth element of this infrastructure, as I said, is the onboard unit. In the onboard unit, we have typical applications, as for example, security applications, which are used to communicate with the PKI infrastructure, ITS applications, which are used instead to encapsulate or to decode CAM and M messages, but also two very novel and important aspects. The hardware security module, which is basically a secure storage place for all the key material that has to be used for communication with the PKI infrastructure, and the anti-hacking device that, as we said, hosts all the applications that are responsible to detect misbehaviors or hacking attempts. As you may imagine, this kind of infrastructure may suffer of several types of attacks. In Caramel, we focus on the one that we believe are the most important ones. First is the recognition of fake message transmissions, where for fake, we mean messages which were not signed, which were signed with old and revoked certificate, or which were replayed by another vehicle but were previously sent by someone else. This is quite challenging because with signed and encrypted traffic, this operation is quite computationally expensive. What we want to do in Caramel is to be able to perform this operation in real time. For the second type of attacks that we deal with in Caramel, instead we try to preserve the identity of the vehicle's owner. In the authorization tickets distributed by the enrollment authority, we do not include the owner identity, but we use pseudonyms. Not only these pseudonyms are modified periodically, so that an attacker cannot track neither such pseudonym in the road infrastructure. Finally, the last type of attacks we consider in this pillar is the modification of the data before being encapsulated in the CAM messages or in the DEM messages by an attacker. This type of attack can be carried out tampering the onboard unit, but also with the so-called GPS spoofing attack. So basically, an attacker make the vehicle believe that it is in a completely different place than the one where it is in reality, so that the payload of the traffic of the transmitted messages is completely wrong. In all cases, our mitigation technique in this pillar is the one of revoking the certificate of the vehicle under attack, so that all the other entities get to know that the data of that specific vehicle cannot be trusted, that cannot be put in input in any of the application that they are running. To conclude this presentation, I would like to focus on the way in which we detect an attack, specifically a GPS spoofing attack, in our project in Caramel for this third pillar. Nowadays, carrying out an attack on the GPS is quite simple, because it's sufficient to have a fake GPS transmitter that progressively increases its power of transmission, so that the GPS receiver in a vehicle is basically tricked in believing that that GPS signal is actually a legit GPS signal, so that it is used together with the other ones in the triangulation operation of the GPS receiver to understand what is the position of the vehicle in the globe. In Caramel, we focus on two possible solutions. First one is on a solution that is based on in-vehicle measurements. And second solution is instead relying on the cooperation among vehicles in the scenario. For the first type of GPS spoofing attack detection, we fuse together onboard measurements, sensor measurements, with a satellite-free global positioning measurement with a GPS-free Kalman-like approach. So we basically do not rely on GPS measurements, so to obtain a secondary location stream that can be compared afterwards with the GPS measurements and for detecting a possible attack. The solutions runs in the anti-hacking device, as mentioned earlier, and specifically the different components work as follows. In order to predict what is the location of the vehicle with a vehicle state model, we use a bicycle model with readings that involve the steering angle, the speed of the vehicle, and its yaw rate. Such information, such prediction is fused together with a satellite-free global positioning measurement, which is based on signal of opportunity. So in the anti-hacking device, we have a passive scanner that aims at specific wireless bandwidths, as for example, radio signals, TV signals, or cellular bandwidths, in order to understand if an active transmitter is present. Whenever there is an active transmitter, the vehicle tries to estimate with a path loss model what is the distance with those transmitters, and with this information obtain, thanks to multilateration, a relative positioning for the vehicle. So how many meters has been traveled by the vehicle from the previous estimation. It's just enough to have an anchor point, as for example, a valid GPS measurement, in order to obtain this satellite-free global positioning measurement, which is used for obtaining the secondary location stream that we talked about before. This secondary location stream is then compared with the GPS measurement with a simple threshold-like algorithm. In this way, basically, if the difference between the two streams of locations is too high, we raise a flag and we say that an attack has been detected. We already have a preliminary implementation of this approach on a drone in our campus, where basically we applied the secondary location stream technique I mentioned earlier. In the figure in red, you have the GPS measurements. In gold, you have instead the secondary location stream. And in blue, you have a possible attack that can be carried out on the GPS measurement with white noise plus a specific average. From our measurements, what we were able to understand is that the 90th percentile of the difference between the GPS measurements and the secondary location stream that we obtain with signal of opportunity is just about of 32 meters. So with this, selecting this 90th percentile as the threshold to recognize a possible GPS spoofing attack, we are able to obtain coarse identification for an attacker that is carrying out a GPS spoofing attack. The second approach that we use in Caramel for detecting a GPS spoofing attack is the cooperative approach I mentioned earlier. In this specific case, each vehicle tries to estimate what is its distance with all neighboring vehicles and its azimuth. This is mainly done thanks to the LiDAR sensor. All those information are not manipulated in the vehicle this time, but they are sent towards the MEC platform we described earlier, together with the GPS measurements. And in the MEC, what we do is to basically try to estimate the location of the vehicles fusing all the received messages. What we do is to run the illustrated minimization. This minimization is basically a minimization of an error function between the expected location that the MEC will basically give in output for the vehicles and the measurements received. Specifically, the difference of the relative positioning measurements that we received by the vehicles and the relative positioning that we obtain with this output of the MEC application. The difference between the azimuth measurements and the azimuth that we can obtain from the expected location that the MEC will give in output. And finally, the differences between the GPS measurements that we received and the locations that the MEC will give in output for the vehicles. In this specific case, what we do is also a small modification, introducing an outlier matrix that mimics the presence of an attacker. So a matrix that can modify accordingly to a given distribution the GPS measurements so to mimic a possible attack. All in all, the MEC gives in output the positions for the vehicle that minimize this error function, and whenever the output of the MEC is higher, the difference is higher compared to the GPS measurement of a given threshold, it raises again a flag and it basically detects the attack. Also in this case, we have some preliminary results, this time in simulation, where we applied a GPS spoofing attack between 100 and 250 meters to the GPS measurements received by the MEC. And what we can say is that our cooperative approach is able in almost all cases to detect the attack and to give in output at the MEC a location for the vehicles which is very, very similar to the ground truth. The only case where we had an error which was as much as 50 meters it was in a case where we attacked simultaneously 4 different vehicles out of 20 that were roaming in the system. But nevertheless, our approach was such that in 95% of the cases, the error was within few meters. So this concludes my presentation. I presented an overview on Caramel and specifically on the connectivity infrastructure that Caramel is proposing for enhancing the security of the communication between vehicles and between the vehicles and the infrastructure. I also presented the mitigation technique that we propose in this pillar, which is basically the revocation of the certificates of the vehicle under attack, and the way in which, for a specific attack, we detect the cyber threat, specifically for the GPS spoofing attack. As future work in Caramel, we aim at implementing a full-fledged version of the described concepts so that it can be demoed with the real vehicles. Thank you very much for the attention, and this is all. Thanks.